Question 1. So this is our modern physics question, photoelectric effect, nuclear fission, and so forth. In an experiment to investigate the photoelectric effect, light of wavelength lambda is incident on a metal surface and current is produced. Always worth sketching a diagram. Current is produced, you have to think where that current is going to. The current is reduced by applying a potential difference V between the metal surface and the collecting plate. Okay, so there's a collecting plate there. This is just a classic photoelectric effect description. So we know photoelectric effect, light comes in, that if it's of high enough frequency, that's going to stimulate, well, it's going to push out electrons, which of course charged particles. They're going to fly across there, at least some of them are. So we then get a charge moving. Charge moving is a current. So that's a current. However, I say the current is reduced by applying a potential difference V between the metal surface and the collecting plate. So if we have a variable source supply, and is it that way round? Well, to reduce the current, we need to repel these electrons away, so we need to make that a negative, so it is that way round, which is good because I just guessed that. And there's a good voltmeter in. Okay. So that's the situation we've got. Classic photoelectric experiment.
Quick point, is your voltmeter?
Hang on. Yeah, I knew there was something wrong there. Let's put an ammeter in there. Is that better?
Yep.
And a voltmeter in there.
Sounds good.
Some of my students take 3 years to work that out.
Yeah. We used to study meters at school and they don't do that anymore either. So it could be a useful thing for scholarship students to look at.
Yeah. Where do you put your bill? Yeah, ammeter in series, voltmeters. I knew that, honestly. Yeah. Right. When the current is reduced to 0, derive an equation relating lambda, the voltage, and the work function of the metal. Right, so what do we know about photoelectric effect? We know that the energy of the electrons is equal to h times the frequency minus the work function. And I'll just look up in the front just to make sure I'm using the same symbols that you're used to, because often these symbols, at university you often use different symbols, different conventions. But so here's our photoelectric equation down at the bottom there. HF equals phi plus EK. So Planck's constant, frequency, work function, K of electrons. Okay, so the key thing about the photoelectric effect is that an electron is emitted due to the incidence of a photon. So some of that photon's energy goes to getting over the work function, the rest goes to the kinetic energy of the electrons. How much energy does a photon have? Well, it depends on its frequency, proportion to its frequency. Okay, so the question's asking about when the current is reduced to exactly 0, what does lambda v phi, what sort of relationship do they have? So, what happens? Current at 0 implies that these electrons are getting just about there, but not quite, before they're turned away. Implies that V. So of course, as the electrons leave, they've got kinetic energy. So they've got kinetic energy here. As they've got here, they've now got electrostatic potential energy. Kinetic energy equals 0 because they've been brought to rest, and then they're off back again. So we know that electrostatic potential energy of electron equals the kinetic energy at which it was emitted. So, charge on an electron times a voltage equals the kinetic energy at which it was emitted. We know from photoelectric effect, EK equals HF minus phi. Just one hint when you're doing math stuff is just to make sure when you're putting in an equation, you're saying where that equation's come from. It's not, so the examiner knows it's not something you made out. You know, boom, photoelectric effect equation in there. Now, what is it we need to relate? We want V. We want work function. We want lambda, not frequency, but that's straightforward because we know frequency and lambda are related. So we know we want to get rid of frequency. Frequency is speed of light divided by wavelength. Frequency times lambda equals c. So EV equals hc over lambda minus phi. So that relates V, lambda and phi. We're given charge of an electron, we're given c. Planck's constant is Planck's constant. There's no doubt about that one. Happy?
The full explanation of the derivation, do you think?
Have I explained fully? I guess really we're using the photoelectric effect equation,
yep,
which is well established. It really comes down to this argument here, isn't it?
Yeah, the energy thing.
So we could say that electrons are emitted from cathode with Ke equals HF minus phi. So we can say V is such that Ke equals 0 when electrons get to anode. So EV equals change in Ke, which equals HF minus phi. Got a better explanation?
Yep.
Or at least.
There's something niggling at me, but I'm not sure quite what it is. No, I think it's okay. Yep.
Am I missing something out there?
No, I think it's fine. I was thinking about how the equation, photoelectric effect equation, your kinetic energy, it would just be 0 in that part of the equation, but it's not because it's still emitted with a certain amount to get to that other plate,
Yeah.
at which point it then has 0.
Yeah.
That would have been the trap for me on this question.
Yeah. So yes, it's not talking about changing the frequency such that, you know, we're used to seeing this graph of the photoelectric effect, aren't we? Here's our frequency, here's the collecting current, and that we can see that or the, let's say the energy, so the energy of electrons. That's your work function. So we used to say, well, yeah, as you turn up the frequency, it comes to a point where something starts kicking in, or as you turn down the frequency, it suddenly vanishes. But that's not what we're doing here.
No, it's a different...
It's a different setup, yeah. So there may be a trap there.
It's
so it's worth just reading carefully what is happening.
It's a typical scholarship question, getting right into the nitty-gritty of what's actually happening, and not relying on a rough...
I guess I have an advantage with this one, because this experiment, doing precisely this, is what one of the experiments we got set up in the labs for the students to do. And it's this precise method that we do to look at the photoelectric effect. Okay, let's go on.